Today we're talking about linear regression, linear models, linear correlation. We're talking about as much as we can talk about. This is going to be our last new content day of the semester. When we come back from Thanksgiving break, we've got one day together on Tuesday, but we don't have Friday because they said no class Friday. So we've got one more day left in the semester. I'm going to leave that day alone. I'm not going to teach any new content next week. It's just going to be a day for you to ask questions, and we'll discuss what the final is going to look like and that kind of thing. But for today, this is our last day where I'm going to present any kind of new information that might show up on your final exam. And we're going to talk about linear models. A linear model is a random process that looks like this. It's going to have a deterministic part and a random part. So the y equals mx plus b is a deterministic function, which means for a given input x, there is one output y. M is the slope of my line, and b is the y-intercept, which is the place where my line goes through the y-axis. Right, you're familiar with y equals mx plus b from Algebra 1 years and years ago. And so I'm using the word deterministic to draw a contrast between like a random variable. There's nothing random about y equals mx plus b. You tell me what the x value is, and then I have a formula to calculate and tell you what the y value is going to be. This little lowercase Greek letter epsilon is going to introduce the randomness. So here, epsilon is the random error, and we are going to assume that it is normally distributed with mean 0. We're not going to make any assumption about what the standard deviation of that distribution is going to be, but we're going to assume that there's a little bit of random error, a little bit of noise here, and it's normally distributed. The mean is 0, so that means the expected value is 0 for the error, but there is going to be some dispersion to it. So this is going to introduce a little bit of noise, a little bit of error into our linear model. And so what I want to do is next is I want to show you what this looks like with an example. And for my example, I'm going to come up with a bunch of x values. And maybe my x values are just going to be the numbers 1 through 20. So these are my x values here in column A. And then in column B, my formula is going to involve some slope and some y-intercept, and then the error term. So let me copy paste that real quick. In column A, I've got my x variables, and in column B, I'm going to have my y variables. Let's say my slope is 1/2. Let's say my y-intercept is 3. So what I'm going to do is I'm going to calculate some y value according to the slope times my x value plus my y-intercept. So when I plug in x equals 1, y is going to be m times x plus b, so it's 1/2 times 1 plus 3, so it gives me 3.5, according to that formula. And I can calculate a y value for all of these x values. And if I graph these with the little scatter plot, that's what my line looks like. For a bunch of different x values, I get a line of y values with a slope of m and a y-intercept of b. We haven't introduced any error yet here, and so now let's go back to my formula, the y equals mx plus b formula, and this time I'm going to introduce some normally distributed random error with a mean of 0 and a standard deviation of, let's say, 1, and see what that ends up. So now when I go to insert my scatter plot, you can tell that it's still kind of linear, right? Like, I mean, everything's still kind of increasing from left to right and mostly aligned. But the normally distributed random error that we introduced is taking each dot and just kind of shifting it one way or another, up or down, you know. And it introduces a little bit of noise. It makes it harder to see what the underlying deterministic thing is. So what we do in statistics, if I want to go back and obtain what the underlying deterministic linear model is we're doing a process called regression. And regression looks like this. If you're using Excel, you click the little plus sign to add chart elements. You click on the trend line checkbox. I know this is super tiny, but there's a checkbox that says trend line for those in the back. And if I check trend line, and then I hit this little button over to the side and I say I want more options, I can tell it that I want to display the equation on the chart. And there it is. So my underlying linear model that I used to create this data had a slope of 0.5 and a y-intercept of 3. These are like the parameters of my model, right? In real life, we don't know the parameters. We want to learn about the parameters. We want to make inference about parameters, but we won't actually know what these parameters are. Instead, we can calculate statistics. We can summarize our data in such a way to make a statistic. And a statistic is an approximation of the parameter. These are our statistics. 0.4771 is our best guess at what the slope is of the underlying linear model, which, of course, 0.4771 is pretty close to 0.5. And 3.306 is our best guess, based on the data, of what the y-intercept is of our underlying linear model. So where the real parameter is 3, the statistic we can calculate is 3.306. And this happens a lot. In real life, if I've got two random variables and I want to see how they are correlated, or how one variable might be a function of another variable, what we do is we assume that there's some kind of underlying function, and sometimes you have to assume what that function looks like. In this class, we're only going to discuss the linear functions, but you could do this with other functions as well. And then add to that some kind of random noise. Because when we take measurements in real life, our measurements are never precise. Our measurements are never exactly accurate. Is anybody taking chemistry, any kind of chemistry course at all? Chemistry lab, stuff like that. Do you discuss this in chemistry? Randomness? Measurement error.
Yeah. A little bit, yeah.
Yeah, like every device you use in chemistry lab, whether it's a scale or a graduated cylinder or anything, a pH probe maybe, like all of those devices have a little bit of measurement uncertainty. If my scale is, my scale is published. if my scale is manufactured by like a competent manufacturer, they will give me a document along with my scale that says, look, this scale is only accurate to plus or minus 0.01 grams. And below that, you can't really trust it, right, to make finer measurements. And so that's based on this idea that scales have a little bit of noise in their measurement that they're going to tell you. And we can't really predict what that's going to be. It's kind of like a random variable. And so another example that's kind of a textbook example is that everybody's height is generally correlated with your foot size, your shoe size. If I know your height, that would help me guess what your shoe size is, right? Like if I know you're 7 foot tall, I might guess that your shoe size is a 15. But if I know that you're 5'5", I could guess that your shoe size is a 7, you know? It gives me information about your shoe size just to look at your height. But that's not the only thing involved in determining the size of your foot, right? Sometimes there's tall people with small feet, and sometimes there's tall people with big feet. Sometimes there's short people with big feet. There's a little bit of random variability to it besides just the linear correlation. So you could do something like that. I'm just going to make up data because I'm not going to measure your feet or your height. But what if I was being a little bit silly? I want to be able to estimate or predict someone's shoe size based on what height they tell me. Well, let's say height is a random variable, normally distributed, and it has a mean of, thinking about inches. What's the mean height in inches? Like 65 inches. And a standard deviation of, let's say, 3. So maybe this is the height of a few students. And their shoe size is going to be, what's the average shoe size? Like an 8. And then standard deviations, maybe like a 2. So I'm trying to think of what the slope's going to be. It's going to be like, I don't know, let's say 1.5 times the height plus 50. Let's see how that gets us. Does that give us, no, minus 50. Let's see if that gets us some reasonable shoe sizes. That does not work. I said minus 50. Maybe it should be like minus 100. Minus 1.5 times 65 plus 8. What's 1.5 times 65? So we'll call it minus 89.5. Sorry, just trying to come up with a model for shoe size. Maybe that should be 2/3. That looks pretty reasonable. Okay, I'm happy with that. So again, pretend this is data we collected between people's height and the size of their foot. if I wanted to make a predictive model, I would just have to slap a trend line on here and then display equation on chart. And then we find like a model that will help us predict somebody's shoe size. So if I'm basing it off of these 7, subjects that are willing to tell me their height and the length of their foot, well, now I can go up to any random person on the street and ask them how tall they are, plug that in here, multiply by 0.6667, subtract 35.33, and I've got my best guess at what their shoe size is going to be. That's kind of how this works. There's a little bit more applicable, less ridiculous examples of why you might want to use linear regression, but it's kind of one of those topics that is it's hard to think of something of like medium importance. You know what I mean? Like, this is obviously not important at all. Nobody would ever want to develop a model that's going to predict your shoe size. That's like a silly kind of toy question. I'm trying to think of an example that's like in the middle of like medium importance, medium complexity. When would you want to be able to predict something based on something else? But honestly, it's like a hard thing to come up with. Like, I've heard of online retailers trying to say like, I can predict how much someone's willing to pay for a product based on how long they spend on the web page. Like, if you were in marketing working for like, I don't know, Walmart or something like that, one thing you might want to look at walmart.com is like, how long has someone spent time on the web page looking at an item? If they are really, really interested in buying these speakers or like a sound bar for a TV, and they spend like 6-7 minutes looking at the web page, reading all the details of the soundbar, maybe they're willing to spend more money for that item than someone who just spends like 5 seconds on the page. And what they're starting to do now, which is terribly unfair and I'm not a really big fan of, is adaptive pricing. Like, retailers like Walmart and Amazon and other places are trying to make it so that your price is different from your price is different from your price is different from your price for different items that you try to buy online. And they'll try to predict the price you're willing to spend for something, because they don't want to sell it to you for less money than you're willing to spend, but they also want you to make the purchase. And so the game is like, how high can they make the price and still have you purchase the item? And so in that context, if you were working for a giant evil corporation and trying to predict that price for people, that's a linear model that you might want to make, is like time spent on web page with price the customer is willing to pay. And those are difficult variables. I mean, time spent on web page is easy, but it's a difficult variable to figure out how much someone's willing to pay for something. But you could look at past sales and how much people spent in the past. You could make kind of a model like this and build it into an adaptive pricing algorithm. On the big end of things, on like the really complex end, is like, what is this thing? This is a house in Olathe. Almost every, this is a bad example. It doesn't have his estimate. Let me go back and pick out another one. Okay, no. What is wrong today? There we go. So I don't know why the first two I picked up didn't work. Do you see this right here? The website Zillow.com is telling me that they are estimating that this property is worth $365,000 and $500. $365,500. That's their estimate of what this house is worth. They're trying to sell it for $443,900, and so Zillow would consider this to be a huge ripoff, I guess, right? because the estimated price is so much lower than the sales price. And that's really important for me as a home buyer because I want to know, am I getting a good deal or not? Well, how does Zillow come up with that estimate? It's really complicated. This is actually a really complicated statistics problem. This is a question that's going to be the focal point of a class I'm offering next year called Regression Analysis, where we just look at regression techniques for an entire semester. But the deal is they come up with their estimate based on the size of the lot the house is sitting on, the number of square feet, the size of the house itself, how much interior square footage is there, how many cars can fit in the garage, what neighborhood is it located in, right? What's the median income in the neighborhood? How is the schools rated? Like what's the rating from the state on the elementary school, the middle school, the high school? The year it was built, that would play into the equation, the number of bedrooms, the number of bathrooms. All of these things are used to create this price estimate, the zestimate. But how do you even come up with that function to begin with? How do you decide how much a square foot is worth? How do you decide how much an acre is worth, or how much a bedroom is worth, or how much a car in the garage is worth? How much a school rating is worth? And the answer is basically regression modeling. And it's, like I said, this is actually a very real world example because I can show you what it is. But this is also the most complex thing we could possibly do because there's so many variables. It's not just one predictor variable and one response variable. Like height and shoe size is really easy to explain because height is the one predictor variable and shoe size is the one response variable. But when you have more variables than just one going on, it becomes a more complicated math problem. But this is still kind of the same idea that we're talking about with regression. And what you would do if you worked for Zillow is you would go back through all of the history of the sales of people selling their home, which is pretty easy to get. You would look at how much the home sold for and what were all of the features of that house. And we could try to make a linear model with just one input variable, one output variable, like square foot to price. But then you'd have a ton of variability because there's so many other factors that determine the price of a home. Okay, so that kind of sets up the idea, what are we doing with regression? I'll see how much of these old PowerPoints I can get through. When we have two variable statistics, we label our variables the response variable and the predictor variable. We also might call the predictor variable the explanatory variable because it explains the changes in the response variable. And we're trying to build a model that can predict the response variable given a value of the predictor variable. Suppose you work for Midland College and you want to determine whether attendance correlates with performance. You record the attendance of each student and you record the exam scores of each student. But if you want attendance to predict performance, I would say the response variable is the exam scores and the predictor variable is the attendance. Here are the types of correlation if you were asked about the type of correlation. This blue example, these blue dots seem to be a linear correlation, and since it's increasing from left to right, this would have a positive slope for the line, so we call that a linear positive correlation. And these red dots, since they are decreasing in general from left to right, the trend line would be a line with a negative slope, so we call that a linear negative correlation. If you look at these green dots, they do not follow a line, increasing or decreasing. Instead, they kind of follow a different pattern. It's still very clearly a pattern. It's just not one straight line. And so we would call that a nonlinear correlation. And if you see a kind of a scattering of points that don't really seem like they follow any kind of pattern at all, that's what we would call no correlation. Then we have the strength of correlation. If all of the dots exactly landed on the line, so there's no noise, there's no measurement uncertainty, there's no error term in our model, that's what we would call a perfect correlation. A strong correlation means that your points are just about exactly on the line, but not quite there. A moderate correlation means you can tell that it's linear, but there is a lot of dispersion. And then a weak correlation almost looks like no correlation, right? Like there's just very, very, very little trace of kind of a linear trend here for a weak correlation. But these are the words we might use to describe that in pictures to go along. We can calculate what's called a linear correlation coefficient. And it's kind of a long formula for a linear correlation coefficient. It involves first taking the z-score for every single measurement in your x variable. I'm using x for the predictor variable. So where it says z with a subscript x, that's talking about a z-score of one of your measurements from the predictor variable. And it also means you have to take the z-scores of all of your measurements from your response variable. And then you multiply these up pairwise, add them together, and then divide by your number of data points. And one pair of predictor and response measurements, one pair is a data point. And so if you're looking for lowercase n, and this is my predictor and response, I would say that n is equal to 7. Even though I understand that there's 14 measurements here, a data point means both. There's 7 subjects, so I say n is equal to 7. So this is a really big, uncomfortable formula. I wonder if there's a way to do that in Desmos. Since you can use Desmos on your test, I wonder if Desmos will calculate a linear correlation coefficient for you. And so I'm going to come up with a predictor variable and punch some numbers into this list. And I'm going to come up with a response variable and put some numbers in the list. And then let's see if Desmos can do something for the linear correlation coefficient. So I'm going to go to functions and see what we have for statistics. Mean, median, min, max, quartile, quantile, standard deviation, variance, covariance, CORR. That might be my linear correlation coefficient. Let's try it out. I think that's it. I think that works. Let me double check because I haven't actually used that before. But let me look up Desmos CORR and see if it, ooh, that's more than I wanted. I'm looking for the Desmos documentation. Okay, well, I guess I can't really find the documentation. Try one more time. Okay, that's right. I mean, at least the AI overview says it's right. So I know that this works in Excel, so let's try this in Excel. 25974. Let's try that. 25974, 1, 2, 3, 4, 5. Let's see if we get the same answer using Excel, and that will answer my question. If I want the correlation coefficient between two data sets. I type in correl. And I'm going to select my two data sets. 0.3511. 0.3511. Okay, so good news, everybody. You don't have to know this formula on a test. Why? Because you can use Desmos Test Mode app on your test. And so instead of having to calculate this, you can go to Desmos, type in your two variables for your two variable statistics, and make sure they match up. The order that you type them in is very important. So like the first number should come from the first subject, the second number should come from the second subject, and then keep them paired up in your data point pairs the whole way. Because that order does matter whenever you type in the correlation coefficient A comma B. It doesn't matter in terms of like I can change the order of my subjects, but I do have to keep the subject's response variable and predictor variable in the same position along the list. That's important. So I've got the correlation coefficient, CORR, in Desmos. And so we were just discussing this. Let's see what it means. How do we interpret the linear correlation coefficient? Well, if I have a perfect correlation, then R is going to equal 1. The linear correlation coefficient will equal the number 1. That means a perfect correlation. If it's strong, you should have an R value that's like greater than 0.9. If it's moderate, then you should have an R value that's greater than 0.7. And a weak correlation would be anything that's like less than 0.7. Just illustrating these. And those aren't like hard and fast definitions and thresholds, but I just want to show you. I really did calculate these R values for all of these points. And those are the R values that I got. You can see what it looks like to have a perfect negative correlation. My R value will be negative for any negative correlation that has a decreasing slope. And so you can see again that R values that are closer to 0 are going to introduce more dispersion in your scatter plot. If the absolute value of R is near 0, we would say there's no correlation. If the absolute value of R is near 0.5, we might say it's a weak correlation. If the absolute value of R is near 1, say we have a strong correlation. Kind of just saying the same thing a bunch of different ways. Do you have questions about this? No? Still makes sense? What if I put pictures on it? Does that still make sense? But you can't have a linear correlation coefficient greater than 1. You can't have a linear correlation coefficient less than -1. It's always between -1 and +1. Okay, I'm seeing what I talked about in previous years. So we can talk about doing hypothesis tests, right? If you have two statistics or two variable statistics, you can do a hypothesis test about whether or not there's an association between variables. And a hypothesis test would look like this. You have to decide ahead of time before you collect the data where you're going to put the cutoff for evidence, right? And so that's kind of like the level of significance, is saying, is it going to be enough evidence to say my correlation is 0.5, or do I need to say my correlation is 0.9 or better? As that kind of hypothesis test. We're not going to do those hypothesis tests on the final exam, but I'm just saying it could happen. In real life, people do those kind of hypothesis tests. Okay, those are just more examples. Let's see what else I have. Oh yeah, this is kind of a good real-world example. When I was a student at Texas Tech, I worked for the dean's office for just a little bit, and at the time they were really focused on trying to make sure that they did two things. They wanted to admit as many students as possible into engineering programs, but they also wanted to have the greatest job placement rate that they could have, right? Like they wanted to have all of their students who started an engineering program to finish the engineering program, and every student who finished to get a job as an engineer. They didn't want to have a bunch of students dropping out. They didn't want to have a bunch of students failing. They don't want to have a bunch of students finishing and not getting jobs. And so they came up with this success ratio, right? And they published it in all of their brochures, all of their pamphlets, everything they did for recruiting. They were trying to say, look, we have this really great success ratio. If you join our engineering program, there's a 99.9% chance you're going to succeed. And that means if they want to keep that statistic up, they did not want to admit any student into the engineering programs unless they thought that student was going to succeed. If they didn't think the student was going to be successful, then they wouldn't let them in. And so what they did, this was the Texas Tech solution, is they said, before you can officially join our engineering program, you have to take a course called pre-engineering. And then based on the data they collected, they looked at students' performance over a number of years, over like 6 or 7 years, and they said, listen, now that we have a few years of graduates, we can compare the students' term grade in the pre-engineering course with their overall chemical engineering GPA at the end of the program, and we'll create a model that will predict the response variable, the GPA at the end of the program, with the predictor variable, the student's term grade in the pre-engineering course. And then they set kind of a minimum GPA standard at graduation, translated that into a minimum GPA standard for the pre-engineering course, and they used that to not allow people into the engineering program. And so let's say this is what it looks like. On the x-axis, we've got the pre-engineering term grade. On the y-axis, we've got their GPAs at the end of the program. And you can see it's kind of linear. It's positive correlation. The correlation coefficient is 0.894. What I'm trying to convince you of now is like, how would we actually calculate what that line should be? When we did this, Excel does the calculation for us, right? Excel automatically calculates what these statistics are going to be, the slope and the y-intercept statistics. But how does it do that? What's built into the program? How is Excel calculating those statistics? How does it come up with this line that passes through the points? Why is that the best line? Isn't there a better line? I don't know. That's what we're discussing right now. So the simplest model would be a constant function. Just saying, I'm going to predict that everybody's GPA is going to be a constant. And that constant would be the mean if I want to minimize the sum of squared deviations. And that's another thing we'll talk about. But the simplest possible model is to say, okay, whatever the student's pre-engineering term grade was, I'm going to assume that their GPA is the average GPA of the graduate, which was, I guess, 45.7. But we want to do better than that. We want to change this line by giving it some kind of slope. And when we give this line a slope, we want to minimize not just these residuals. By the way, this is the definition of the word residual, is like, what's the difference between a measured value and a predicted value from my response variable? So it's like the vertical distance in this case. That's my residual. And this is how we give it a slope. If we look at the residuals now, the residuals are a little bit less than they were before on average because we're getting the line closer to the dots. So if we want the best linear model, we're trying to optimize the problem. And in mathematics, optimizing means we are going to either maximize or minimize some criterion. The criterion we're trying to minimize is called the sum of squares total. And if I were just using the flat horizontal line, the sum of squares total would be my measured y value minus my mean y value. And it turns out that the mean minimizes the sum of squares total. But we are not just trying to have a flat line, we're trying to minimize, I guess I just don't include it here, okay. It's been a few years since I taught this class. I think I did a lot more back at Midland College than we've been doing here. But okay, solving this optimization problem means like minimizing the sum of all the squared residuals together. That's our criterion that we're trying to minimize during this optimization problem, is take the residuals, square them, add them all up. That's what we want to minimize. We want the residuals to be small. And when we do this, it's a long mathematical derivation, but you don't need to know it. The slope, the number that multiplies x, the slope is going to be the linear correlation coefficient times the standard deviation of your y measurements divided by the standard deviation of your x measurements. That's going to be the slope of my regression line. And then the constant term at the end, the y-intercept, is going to be the sample mean of your y measurements minus the slope times the sample mean of your x measurements. And again, I think this is something that Desmos can do for us. But you got to pay really close attention here if you want to be able to do this the Desmos way. Here's the Desmos way. If I say A is my predictor variable, and I'm going to make this 1, 2, 3, 4, 5 for right now, I can plot all of those points on Desmos by typing in parentheses A comma B, so that A is my list of x coordinates and B is my list of y coordinates. And so here's the points 1, 2, 3, 4, 5. I want to give this a little bit of error to it, right? I don't want it to be exact. A little bit of something else. To make it so that it's not just super clear cut. But again, typing in parentheses A comma B here is going to plot all the points for you at once. And then the Desmos way of finding the regression line is to say B tilde MA plus, I'm already using B. I'll call it C then. Okay. This is how you get Desmos to do your regression for you. You probably want to use this on the final exam, right? B tilde MA plus C. And what this tells Desmos is like, I've got these variables A and B, and I already put those in a list, right? A and B are containing my predictor variable, response variable. And I'm telling Desmos with the tilde that I want a model that looks like B equals MA plus C, but the tilde is saying, even though I want B equals MA plus C, I recognize that there is going to be a normally distributed error term in here. And so it's not going to be exactly equal to. The tilde means like approximately equal to. And Desmos is going to do the work of finding the regression parameters, the slope of this line and the constant term of this line, the y-intercept, that's going to best fit these data points. And best fit, again, means we're taking the residuals, the distance between the point and the line is the residual. Take the residuals, square them, add them all together. That's what we want to minimize. And this is the line that minimizes the sum of squared residuals. And it's going to tell me my linear correlation coefficient. This little lowercase r is my linear correlation coefficient, 9762. Because I changed some of the numbers, so now it's 9762. It's a pretty strong correlation. And it gives me one other thing. That one other thing is capital R squared. And this is called the coefficient of determination. It's a very fancy name. Let me see if I can find my slide about coefficient of determination. Okay. This is the thing that I want you to know. We'll zoom in so I can get rid of all the excess stuff. Oop, wrong slide. This coefficient of determination is a ratio of the explained variation divided by the total variation. So when it says total variation, it's talking about for each one of these data points, they're like dispersed in the vertical direction. There's a lot of variation in the vertical direction. When you look at that scatter plot, big cloud of points. That's the total variation. The explained variation means like what fraction of that total variation is explained by the linear model. Whenever I draw a linear model through the points, I've, quote, explained some of the variation with my model because instead of just going from the mean way up to each point, I'm just making a smaller trip from the predicted value of my linear model up to that point. And that's the ratio that is described by the coefficient of determination. It's telling me how much of the variation in my response variable can be explained by my linear model. So do we want r squared to be a big number or a small number? I want my model to do a really good job at explaining. I want my model to have a lot of explanatory power. So that means I want the explained variation to be big. It can't be more than the total variation, so the maximum value of r squared I can get to is 1, but I want my r squared value to be really close to 1. An r squared value that's really close to 1 means it's a good model. So r squared is going to be the ratio of explained variation to total variation. And we want our model to be able to explain as much of the variation as possible. So while my r squared value has to be strictly between 0 and 1, we want r squared to be as close to 1 as possible. How about that? If r squared is equal to 1, that means my linear model explained all of the variation. And if my r squared is 0, that means my linear model explained nothing. And the coefficient of determination is related to the linear correlation coefficient. In fact, it's just the linear correlation coefficient squared. It's pretty easy to remember. R squared is equal to r squared. I don't know why the coefficient of determination is capital R squared while the linear correlation coefficient is lowercase r squared. That's not a choice that I made. That's just a choice that statisticians made a long time ago, and all of the textbooks and all of the software have stuck to that convention. Like, for example, when I switch back to Desmos here, you can tell that Desmos gives us these statistics. They give us the coefficient of determination as capital R squared and the linear correlation coefficient as lowercase r. But if I take the lowercase r number and square it, I take 0.9762 and square it, it's going to give me 0.953, which is the coefficient of determination. So Desmos is telling me then that about 95% of the variation between the y values of these black dots here on my graph, 95% of that variation is explained by this red line. There's still a little bit of variation that's not explained. That's why the dots don't fall directly on the line. But most of that variation is explained well by that red line. How much? Exactly 95.3%. That's kind of a cool statistic. The moral of the story is you want your r squared to be close to 1. If you were reading a study, for example, like you're doing your statistics case study assignment, and you pull up an article, and the article says, listen, we developed this linear regression model, and our r squared value was 0.6. You would say, ooh, that's not really a lot of evidence, right? Their model only explains 60% of the variation that they saw. So it probably means that, it could be just a spurious correlation, like something that doesn't really imply a cause and effect thing. Or maybe there is some kind of cause and effect, but there's other factors at play. Like, I could make a correlation between, I don't know. I always find it really easy to come up with like public health examples. I don't know why. It just seems like the easiest thing to reach for. But I could try to make a correlation between like the number of cans of soda consumed per week and an adult's BMI or something like that. And probably, just taking a guess here, I haven't looked at the data, but I'm guessing probably if an adult consumes more full sugar sodas in a week, maybe that correlates with having a higher BMI. But there would clearly be a lot of other factors, right? That is not the only factor. And so that might only explain 40% of the variation. It wouldn't be a very strong R-squared value because there's so many other factors like sleep and exercise and the rest of your diet that has to go into your BMI, your genetics, a whole bunch of other stuff. So it's not going to explain very much of the variation. A high R-squared value means you've got it cornered. You're almost definitely looking at a cause and effect relationship because it does so well at explaining the variation. And that's it. I mean, I'm tired. I want to go home. I want to start Thanksgiving break. So, do you guys have any questions? I'll come up with some kind